Hello everyone. The object of this video is to present Riemann integrable functions using Darboux's theorem. First we will define Riemann upper and lower sums of a bounded function defined on a closed interval AB. We can see here the interval AB on real line can be divided into non-overlapping subintervals, and the points of these subintervals can be taken in a set, and this set is said to be partition. And one can see that the length of a subinterval is here delta 1, we can say delta 2 and delta n, and sum of length is b minus a, and these points are in a particular order. You can see x0 is less than x1. In this way we can find a partition of this interval AB. Since function is bounded in this closed interval AB, so it will be bounded in every subinterval of AB, and therefore we can assign greatest lower bound and least upper bound of the function in these subinterval also. Corresponding to these greatest lower bound and least upper bound, we can define upper sum and lower sum of a function with respect to the partition P. The upper sum of the function f with respect to partition P is the sum of all values uk delta k from k is 1 to n, and lower sum of function f with respect to partition P is sum of lk delta k from k is 1 to n. So corresponding to each partition P, we can find an upper sum and lower sum. Norm of P is a real number which is assigned as a maximum length of subintervals defined on this interval AB. So this is the maximum length, and that length, if you see the number of partition of this interval is n there, and as the number of partition increases, the length of subinterval decreases. And it can be seen that upper sum is defined corresponding to value the greatest lower bound value of the function in each subinterval, and lower sum is defined corresponding to the value of greatest lower bound in each subinterval. Therefore lower sum is less than upper sum, and therefore the difference of upper sum with lower sum can be seen as uk minus lk delta k. Refinement of a partition. A refinement of a partition is a partition of the interval AB which contains all points of P. So Q is a refinement, then it contains all point of P. Q will be proper refinement if it contains more points than P. If there is a point Q in Q which is not in P, in this case we say that Q is a different from these points of P, and therefore there exists an interval in which Q lies in such a way. So here we can see that there is a refinement Q is defined corresponding to partition P. There is already partition x0 x1 xk minus 1 xk, and Q is a point which is not in P and is in Q. So there will be a point on this number line between somewhere xk minus 1 xk, and therefore this length will be length of the subinterval is delta k dash, and this length will be delta k double dash. One can see that delta k dash and delta k double dash will be less than the length of the interval xk minus 1 xk, means delta k, and therefore we can say that the refinement, if we take more points in refinement, then its norm will be reduced. So corresponding to this subinterval xk minus 1q, the function is bounded, and hence the greatest lower bound and least upper bound values of function can be defined in each new subinterval also. So there is a observation, q is any partition of p, then the following conditions holds. These are interesting because on the basis of these conditions we will define upper integral and lower integral, and hence the integrable function. Okay, you can see here lower sum of a partition always less than equal upper sum of the partition with respect to the same partition. But here we see that q is a refinement of p, so the lower sum of partition p is lesser than the lower sum of the partition with respect to partition q. And there is a reverse situation in case of upper sum. You can see that upper sum of partition q is less than upper sum of partition with respect to partition p. So as we take partition of a refinement, as we take a refinement of some partition p, then lower sum upper sum increases corresponding to refinement, and the lower sum increases corresponding to refinement, but upper sum decreases corresponding to that refinement q. So you see there that p is a q is a refinement of p, but here upper sum of corresponding to this refinement is lesser than upper sum corresponding to the refinement p, and here the lower sum with refinement p is less than lower sum of refinement q, which is a refinement. So as we take part refinement, lower sum increases, however upper sum decreases. On the basis of this, one can observe that the set of all upper sum, the set of all upper sum which is bounded below by each lower sum, you can see that this is there is a upper sum which is bounded below by lower sums. So set of all upper sums is bounded below by each lower sum, and the same way the set of all lower sum is bounded above by each upper sum. You can see that this is the arrangement. These inequality implies that the lower sum cannot exceed some upper sum. Using this concept, we define upper and lower integral. We have seen that the sequence of all upper sum is monotonic decreasing and bounded below by each lower sum, and same way the monotonic increasing sequence of all lower sums is bounded above by each upper sum. So by monotone convergence theorem, these sequence will converge to their infimum, means that the sequence monotonic decreasing sequence of upper sums will converge to greatest lower bound, and the sequence of lower sum will converge to least upper bound. So corresponding to this collection of upper sums and lower sums, there exists a real number which is infimum and supremum. So infimum of all upper sum is called upper integral, and we denote it by this integral. Here we see that this is an integral, and we are making this different by taking this line b bar, taking this in same way. Supreme of lower sum is called lower integral, and it is denoted by in this way, this integral, and we are taking here bar here also. So this is upper integral and this is lower integral. Now Riemann integrable function means A real valued function f defined on a closed interval is said to be Riemann integrable if upper integral is equal to the lower integral. So it means that a function is integrable if upper integral is equal to lower integral. In this case, we say function integral exists. This integral from a to b fx dx exists, and the common value is equal to the common value of upper and lower sum. This is an interesting example here. We From the construction we can see Riemann integrable function is bounded, but a bounded function need not be Riemann integrable. So this is the shortcomings of Riemann integrable, and therefore it has a this can be applied on limited functions defined on a closed interval. Uh, Here we see that function is bounded in this interval AB, however, it is not Riemann integrable, because when one will compute lower sum, then it will be 0, and when it will anyone compute upper sum, then it will be b minus a. So upper sum is a constant sequence and lower sum is also a constant sequence, and a different, so their supremum and infimum will be different, and therefore this function is not Riemann integrable as per definition of Riemann integrable function. Darbou's theorem is an important theorem in proving Riemann integrability on the basis of partition. So first one, we observe that if we are taking epsilon greater than 0, then this is the supremum of all lower sum, and therefore by definition of supremum, if you take epsilon from it, then there will be a lower sum greater than that. And in similar way, this is the greatest lower bound, this upper integral is the greatest lower bound, and if you add some epsilon in it, then there will be an upper sum. So there may be some partition p1 and p2, but we can take p as a union of p1 and p2. So these two inequality can be hold for same partition p. But in Darbou's theorem, it is stated that there are infinite many such partition with a restriction on their norms. So we can find infinite many such partition which satisfying these conditions. So this is Darbou's theorem. F is a bounded function defined on a closed interval AB. So if we take epsilon greater than 0, then we can see that the above conditions, these conditions stated here, also holds for all partition P with norm less than delta. Before giving proof of Darbou's theorem, first we will prove this result here. This result is saying that we have seen that in previous slides, when we take refinement of a partition P, then lower sum increases corresponding to the refinement, but there is a difference. What kind of number can be taken, so can be added in lower sum, so that will exceed from the lower sum of the refinement. And in similar way, what number should be subtracted from upper sum corresponding to partition P, so that the upper integral will exceed from that. So this is a very easy to see here. This is by definition of lower sum and upper sum. We will do this result for lower sum only, and it will follow for similarly for upper sum. So we take Q be a partition refinement of P, and obviously we are taking a point Q in subinterval xk minus 1 xk for non-trivial case, and in this way we will find two subinterval of an interval xk minus 1 xk, and function will be bounded in these two subinterval also, and we can define lk dash uk dash lk double dash uk double dash as a greatest lower bound, least upper bound of the function in their respective subintervals. And one can see that this is the greatest, this is lk is a greatest lower bound of f in subinterval xk minus 1 xk, and it will be smaller than lk dash, which is a subinterval of xk minus 1 xk. So after considering all these symbols, we take a lower sum with respect to partition q, and lower sum minus lower sum with respect to partition p. So we see that we are considering only one point here. So we see that the rest of subinterval will give the same number, L k delta k, except this subinterval xk minus 1 xk. So we can not take consideration of these subinterval which has no new points. So we see that this is a new point in this interval xk minus 1 xk, so the function will have something in it. So you see here, this is a lower sum corresponding to the refinement q. So refinement q will have two subinterval here. Length of first subinterval is q minus xk minus 1, this is here, and the greatest lower bound value is lk dash, and second subinterval is q xk, and length of this subinterval interval is xk q, and here is this, and this is the greatest lower value, and this is the length delta k xk minus 1, and the value of greatest lower bound in this interval xk minus 1 xk is lk. Now we add here q and subtract q, then and taking common q xk minus 1 here, and also here you find one finds that this and this, and you see this quantity is lesser than. If you replace, we see that function is bounded, so function is bounded by k, so the maximum oscillation of this from this here expression here, the maximum oscillation will be 2k, so we can replace this value by 2k, and here 2k, if we take common 2k here, then it will be xk minus 1 means 2k delta k, and delta is norm, so delta k will be smaller or smaller than delta, so this is 2 delta k. So you see, one can see here k is a bound of the function, and delta is the norm of the partition. So if we consider all these things, then we can find this result. F is a bounded function on interval ab, P is any partition of AB. If fx can be the absolute value of fx is less than equal k for all x belongs to AB for some real number k, and q is a refinement of P with norm of P less than delta, where delta is a real number. So in this situation we find that lower sum of corresponding to refinement less than equal lower sum of the partition P plus 2 delta k. So this is an important result for proving the next proof of Darboux's. Let epsilon be greater than 0 be given. So by definition of upper integral, there exists an integral such that uf p1 less than this because this is the greatest lower bound, and if you are adding something in it, then there will be a upper sum which will be smaller than that. So we call this equation 1, Now we assume two things. P1 is a partition of AB, so it will contain some points. We say it has n plus 1 points, so P1 has n plus 1 subintervals in x I minus 1 xi of AB, and we also can assume the function, as function is bounded, so we can assume a positive real number satisfying this condition also, as we have discussed earlier. So now we choose delta that will work for our partition P, and we also consider, after defining this delta, we can consider a partition P, because this is a given number, and we can, it is always possible to assign a partition P here, whose norm is less than the given number. So this is the less than delta. So now we consider, we have two partition P and P1. So P partition P has norm less than delta. So let Q is union of these two partition. So obviously Q is a refinement of P, and which has at most n minus points other than points of P. As we know that there is a two partition P and P1, so, and P1 has n points, and we know that there is 2 points common in it, and there may be more point common in it. So therefore the number of partition, number of points in Q can be n minus 1 points other than the points of P. Now we apply the proportion that we have discussed earlier. So in this case Q is a refinement of P. Then we have already discussed that the UFP will be greater than equal UFP, UFQ will be greater than equal UFP minus 2n minus 1 delta K. Please note this point here, because we are taking, we are applying proportion 2 here repeatedly, because first it contains 1 point, then it will be 2 delta K. If it contains 2 more points, then it will be 4 delta K, and it has n minus 1 more points, then it will be 2n minus 1 delta K. So this result is a repeated application of proportion 2. So this result now we have, and on the basis of this result now we start from here UFP1, and we know that Q is a refinement of P1, and we know that corresponding to refinement, the upper sum, value of upper sum will be lesser. So this is UFQ here, and from here we see this is UFP, this minus 2n minus 1 delta K, and this is, now we are taking the value of here, this is value. If you are replacing this value, then this will have, okay, this is now applying this expression 1, applying this expression 1, you will see here this expression. From here UFP1 greater than UFP minus epsilon by 2. Now from here you can see UFP is less than UFP1 plus epsilon by 2, and from expression 1 here this inequality appears after substituting the greatest larger value of UFP1. So this proves the result for upper sum, because there is a partition P whose norm is less than delta, and there are infinite many such partition. In similar fashion we can prove the result for lower integral also. So now we will discuss the integrability criteria. Epsilon greater than 0 be given by Darboux's theorem. There exists a positive real number delta, and each partition P of AB whose norm is less than delta will satisfy these inequalities. and these inequalities. Now if you take upper sum minus lower sum, so upper sum minus lower sum, if you take minus LFP less than minus lower integral plus epsilon by 2, and if you are adding all these two things, then you will have epsilon plus epsilon. So this is epsilon value here. So if function is, if you are taking function is integrable, so this up lower integral and this upper integrals becomes identical, and if you, when you subtract these things, then their value will be lesser than by epsilon by 2 plus epsilon by 2, which is epsilon. So this is very easy. Now conversely we can consider there are infinite many such partition P whose norms was less than delta, and their difference of upper sum and lower sum is less than epsilon. Now we know that this is upper integral, and upper integral is the greatest lower bound, so it is a lower bound. So every uh, upper sum will be greater than or equal to this. Now, and this is less than, this is from this given condition, this is less than LFP plus epsilon, and we know that LF, this is supremum value. So if you take this value, then resulting inequality will be greater, so this will be plus epsilon. So you see here, this is upper integral and this is lower integral plus epsilon. So this difference, now if you take this difference, then you will find that this is non-negative difference with less than epsilon, as we have taken epsilon is how small. So by this condition we find that upper integral is identical to lower integral, and it was the criteria of, it was the condition of Riemann integrability. So we have this necessary and sufficient condition for Riemann integrable function. A bounded function f defined on a closed interval is integrable if and only for each epsilon greater than 0 there exists a positive real number delta such that the upper sum minus lower sum less than epsilon for every partition P of AB with norm less than delta. In previous video we studied a necessary and sufficient condition for Riemann integrability, in which we considered epsilon for greater than 0 and there exists a partition P for which this holds. So this condition is much stronger than that previous condition. So in this video we studied Darboux's theorem and the integrability condition based on Darboux's theorem. In next video we will study Riemann sum, and we will discuss some special kind of Riemann integrable functions, continuous function, monotonic functions, and discontinuous function with finite number of point of discontinuity. And these are the books can be useful for students. Thanking you for listening me carefully.